and start sharing, because that's what I do, I share. Okay, so the last part of this chapter 15, not much mathematical, a little bit though. So I thought we'd talk about hyperbaric medicine a little bit. You know how it treats the bends for diving accidents. It can also treat anaerobic bacterial infections. So I was talking to the guy who used to run it. I think he's since left. But he would be able to put patients with gangrene and other flesh-eating type bacterial infections. These are anaerobic bacteria. So he could put them at 100% oxygen at 3 atmospheres for a short period of time. That would give you a partial oxygen pressure of 3 atmospheres, which is pretty huge, because right now we're at 1 atmosphere and it's about 20% oxygen, right? So right now we're about 0.2 atmospheres. So anyway, and so the partial pressure of CO2 in expired air is 29 torr. If the atmospheric pressure is 1 atmosphere, what is the percent oxygen in expired air? Well, the only thing you have to do is make sure your units match, right? So 29 torr out of 760, or 0.038 atmospheres out of 1 atmosphere, because 29 torr is 0.038. So it's about 3.8% CO2 in expired air. And predicted directions of gas diffusion. Well, gases always go from a high concentration to a lower concentration. Why? Well, kinetic theory will tell us because gases are always moving. That's what would happen with random diffusion, right? Random movement. And gases are mostly empty space. That's why one gas can diffuse through air. So if the partial pressure of oxygen is 160 torr in the air, 100 torr in the blood, then it's going to go into the blood. And I simply converted the torr into percent just to show you that, yeah, you can use either torr, you can use partial pressures in any manner you want, also in terms of percent. So partial pressure of CO2 is 50 torr in the blood, it's 35 torr in the tissue. Where's it going to go? Into the tissue. And you may be thinking, well, we don't want that. And you know what nature is thinking? Oh, we don't care about you because we don't know you exist. We're just nature. That's what gases do. So here's another one. If it's 4.1% in the air, 3.3% in the blood, then it's going to go into the blood. And then if you're looking at different gases, guess what? You cannot tell because they diffuse independent of one another. So in biology, here's what happens to most of us aerobic organisms. Thanks to plant activity, there's a high partial pressure of O2 outside of us. That's what causes O2 to diffuse into our body. Do our lungs make that happen? No, they don't. All they do is make it happen more quickly. But it wouldn't happen unless it was high out here and lower inside of us. And then during the process of metabolism, we breathe in oxygen, we convert it into CO2. That's why oxygen keeps coming down its concentration gradient. But then we're producing carbon dioxide, and it's higher in us than it is outside, which is why it now leaves our bodies when we exhale. So if we look at fresh air versus expired air and say, here's somebody, let's follow the oxygen. So in fresh air, it's about 160 torr in average in the lungs at 1 atmosphere pressure is about 100. That's why it goes down here. And the blood comes into your lungs and it picks up approximately that concentration. This is now in the air in your lungs. This is actually dissolved. What is it dissolved into? Much of it is dissolved into the hemoglobin, which even makes it more soluble. So then it goes to the tissue. And in the tissue, oxygen is being converted into CO2. So it's pretty low in actively respiring tissue. So it will go from the blood to the tissue. And as it leaves the tissues and goes back to the lungs, this is where people get confused. Wait, it goes from 30 to 40? That doesn't make any sense. No, that does make sense, because the blood doesn't come to the tissues and then just stop and say, okay, everybody out. You may have noticed if your blood stops circulating, you're kind of like dead and stuff. So it's not completely removed. Then it gets into the lung alveoli again, and then it gets replenished, right? Comes down the gradient again. And CO2 is low in fresh air. Notice that it's fairly high in the lung tissue, in the lungs volume, I should say. So then it's about 40 in the blood that leaves the lungs. It gets higher because of the tissues. Doesn't go completely 100% efficiency from tissues into the venous blood. Again, not 100% efficient, but it leaves an expired air is much lower than what's in the lungs. And if you look at partial pressure of water and nitrogen, that has to adjust because the total pressure has to stay the same, right? So here's some typical clinical blood gas values. And so partial pressure of O2, they sometimes call it that. CO2, pH, oxygen saturation, bicarbonate, because this has to do with your blood pH. So is this. This is your actual pH. This is your buffering capacity that we'll learn later on. And anyway, so I saw this one time and I thought, oh, that's really immature. I like it. So I thought I would share it because that's what we do. And then this one. Have you guys ever smelled a skunk? It is absolutely just the worst smell. Remember one time I was on the mainland, I was going to go visit my one sister. So I had my wife, the kids in the car, windows rolled up, the air conditioner on, and we must have passed a skunk. I never saw a dead skunk, nothing. But it came into the car and we had the windows rolled down for the next several hours. Just terrible.
It sprayed in the car?
No, I never saw a dead skunk or anything. We just passed by some part of the woods and the skunk all got in the car somehow.
Yeah, that's dangerous.
And then, you know, you always hear about dogs messing around with skunks, right? And so my other sister who I was visiting, they also had skunks over there. And somebody's dog had messed around with a skunk and came home smelling like a skunk. And so I'm trying to tell them, you know, tomato juice, any kind of oxidizers, whatever. And then I asked them, well, you know, how much is a new dog? They didn't like that. And that's it for this chapter. So any questions at all? Okay, so chapter 16, there's a lot of short chapters in this. Somehow I have the propensity to take a short chapter and make it long, called words. So this is about liquids and solids. And so most people know this. If you have, say, ice, solid, you put in heat and you melt it. And then when the liquid turns back into the solid by removing heat, we call it freezing. And another word for that is fusion, where the particles, whatever they are, fuse together to make a solid. And of course, liquid water can vaporize and then condense, right? And most people don't know about this. So there's several solids, many of them actually. Ice is one of them that can simply sublime. I remember on a trip visiting my sister again. There was snow. That was the first time I'd ever really skied in snow. We had to do that just to get through their house. And the next morning, it never got above like 0 degrees centigrade, but the next morning, so much of the snow was gone. It simply went from the solid to the gas. It vaporized. It's called sublimation. And if you think about it, what is rain? Water vapor condensing into liquid. The liquid is more dense, then it falls down. Hail, from the gas to the liquid to the solid, and then it falls down. Snow is when you go directly from the gas to the solid in a crystallization thing, also known as deposition, and then it falls down. And phase diagrams are kind of interesting. So here's a general one. So here's the gaseous state, here's the liquid state, here's the solid state. So you can see sublimation happens here, vaporization, condensation here, melting and freezing up here. And then we have a triple point. The triple point is the temperature and pressure where all three of the phases exist at the same time. And immediately we'll look at water. Here's the triple point for water. And I don't know why I use the red donut. I do things sometimes, I don't know why. But that represents the temperature that we're at right now in the pressure. So that's where we are right now. So you would expect to find water in the liquid phase. Then if you were to lower the temperature down to 0, what happens? Oh, it transitions into the solid phase. And if you raise the temperature to 100, then it transitions into the vapor phase, right? The gaseous phase. So does the triple point exist on planet Earth? And I've never seen anybody explain that. And the answer is no, it doesn't. The triple point for water would be near 0 degrees Celsius and an extremely low pressure. Mount Everest is right here. So you can see that, no, we're not even near the triple point. Couldn't get there. If you're at Mount Everest at this particular pressure and you simply raise the temperature trying to get to the triple point, you'll never get there. And another thing that's interesting, in aviation, they talk about the Armstrong limit. That's the altitude where human body fluids boil. So we're right here. And what happens when you go extremely high? The pressure starts to decrease. And at some point over here, notice liquid, whether it's in your body or not, transitions directly into the vapor phase and you'd be dead. That's why you need pressurized suits, as well as temperature control, right? And then here's something kind of interesting. So, diamond. What does it take to make a diamond? So here's the the area where diamond is, look at the pressure. It's extremely high pressure. Here's where we are. So it's extremely high pressure. The temperature doesn't have to be that high. A lot of people say, oh, it takes high pressure. Well, no, look at the phase diagram. So here's the triple point for diamond. But what would happen if we took your diamond and we melted it? Like, hey, let's take your diamond that you love and everything else, and we'll see if it melts, because you would think it would go right back to being a solid again, right, when you take the heat away. Well, the answer is no. You're down here. If you were to melt it, first of all, what would happen to it? It would go directly into the vapor phase. And then if you cooled it back down, you wouldn't end up with diamond anymore. You'd have graphite. See how that works? So one time I forget what anniversary it was, or 20th anniversary or something, and my wife teaches chemistry and physics, or she did. Now she's more of a vice principal. So I decided that I wouldn't give her a diamond, I would give her a pencil. You know, because pencil has graphite as the lead in there, right? Yeah, it didn't work very well. I was trying to explain to her that, you know, blood diamonds, people suffer to get them, and graphite is more stable anyway. So the saying has always been, a diamond is forever. What do you think? Here's a diamond, and here's the conditions that we live at. No, graphite is forever, not a diamond. And here's carbon dioxide. So here's the conditions that we are right now. So how do you make dry ice? To get into the solid form, you would have to lower the temperature way down here. So the pressure is not that important, but what's important is that super low temperature, right? We use carbon dioxide, we make it into a liquid. So that means that you pressurize the gas into a liquid. You don't necessarily freeze it. And then we can use that as a very good solvent for removing non-polar things like caffeine from coffee and things like that. Then when you want to get rid of the solvent, you just open it up and let the gas escape. So most of this chapter is about phase changes and the energy that's involved in that. So we have the specific heat of the solid, the specific heat of the liquid, and the specific heat of the gas. Now we did calculations, I think it was chapter 3, maybe chapter 2, I forget. We did these calculations, specific heat of the liquid, before. Does that look familiar to you? How much energy must be removed to cool 2 grams of water from 25 to 15 degrees? So there's our conversion factor. We need to get rid of grams, get rid of the temperature change, and we got the number of calories. So now we're going to look at the specific heat for the other phases. So the specific heat of the solid phase is the energy required to heat or cool a solid. In other words, to change its temperature. So the specific heat of ice is about 0.5 calories per gram per degree Celsius. You do not need to memorize that, but you might need to do some calculations with that. So how much energy is required to heat 2 grams of ice from -15 to -5? So there's the conversion factor. Get rid of grams, get rid of the temperature change, right? And all you did is just change the temperature. So the specific heat of gas is similar, different number, but it's similar. And then What's new is we're going to look at the energy used to change the phase. And this happens at the same temperature. So we find that it takes 79.9 calories to melt 1 gram of ice. It starts off at 0 degrees. It ends up at 0 degrees. The only thing that's different is you melted it. So here it took 160 calories. Notice that we're just looking at the units. Okay. And then the heat of vaporization, going from the liquid to the vapor phase. So notice that you have water at 100 degrees. You put in this heat energy and you get vapor at 100 degrees. But look at the size of this number right here. It takes 539 calories to vaporize 1 gram of water when it's already at 100 degrees. And then we'll put all this together in what's called a heating cooling curve. I put a whole bunch of information on here so you get a perspective. Thinking about water, in the solid phase, you have about 4 hydrogen bonds on average. In the liquid phase, you have about 2 hydrogen bonds. So when you're melting and changing the temperature of water, what are you doing? You're breaking attractive forces that we've called hydrogen bonds. And then in the gaseous phase, there are no attractive forces. So again, you're breaking more hydrogen bonds. Here are the conversion factors. And here's what happens to the particular substance, this being water. So, first of all, how cold can water be? Anybody know? Maybe 0 degrees Kelvin, which is minus 273.15 Celsius.
No.
So your freezer compartment for your refrigerator is about minus 20. So it's about right here. Say you take the ice cubes out of your freezer. What temperature are they when they're in the freezer? Be minus 20, right? So you put them on a countertop, and what's happening? Heat energy is going into the ice, causing the ice to increase its temperature. Then after a while, the temperature is at 0 degrees, but it just stays there for a while. Oh wait, you're still putting heat energy into there, but it's not changing the temperature. So what is it doing? That heat energy is being used to break attractive forces. Make sense? And then magically, you're watching it, it's 0 degrees. Here it's 100% solid. Here's 50 solid, 50% liquid. Now it's all 100% liquid at 0 degrees. And now magically, if you add more heat energy, the temperature of the water increases. Then you get to 100 degrees. And you keep putting heat energy in, and the temperature doesn't change. Water boils at a constant temperature, doesn't it? But if you're putting heat energy in, then temperature isn't changing. What is happening? Well, you're converting the liquid into the gas. You're breaking the rest of the hydrogen bonds. So here we're at 100% liquid at 100 degrees, 50% liquid, 50% gas at 100 degrees. Here we are 100% gas at 100 degrees. And magically enough, if you increase the temperature if you add more heat energy to the gas, the temperature goes up. And look at the conversion factors. Notice that temperature is in here and it's not in here. Why? Here the temperature changes. Here it doesn't. Same thing here and here and here. Well, what would the problems look like? How much energy is required to heat 100 grams of ice from minus 20 to 140 degrees? I would beg you to use this as a cognitive map, something to help you understand where you're starting from, where you finish up at. So what do we need to do? We're about here at about minus 20. We got to heat that ice up. Here's the calculation for heating the ice. Now I'm here. What do I have to do? I got to melt the ice. So here's another calculation. Then what do I have to do? I got to go from 0 degrees to 100 degrees. Notice that there's a 100-degree temperature change here. Here there's no temperature. Here was a 20-degree change. And then I got to vaporize it. I got to go from here to here. This is where the biggest value is, right here. And then I got steam at 100 degrees. I got to get it up by 40 more degrees. So another temperature change of 40. And then I just simply add them all up. So what we're trying to do is we have to calculate 1, 2, 3, 4, 5 steps, but what we really want is the total amount of energy that there in the blue. So we have to add all those up. I know you can do this math. It's simple math. And you don't have to memorize any of these conversion factors. But think about this. 100 grams is about 100 milliliters. I don't know if I have a... Here is a 50 milliliter graduated cylinder. So we're talking about 2 of these. Look how much energy it takes to take 2 of those from minus 20 all the way up to 140. About 75 kilocalories, but that's about the same amount of energy as 1 or 2 bites of a McDonald's cheeseburger. And people wonder why they gain weight. Think about it. 2 of these solid in your freezer. 1 or 2 bites of McDonald's cheeseburger will vaporize this to steam at 140 degrees. Does water ever wear out? Say you take water, you freeze it, you boil it, you freeze it, you boil it, never wears out, right? So all these processes are completely reversible. But here's why I want you to draw the heating cooling curve out, just sketch it. Because look at this question. This is more like something you'd have on an exam. How much energy is required to heat 100 grams of water from 37 to 140? I don't need this whole thing. I only need from 37 up to 100, vaporize it, and then from 100 to another 40 degrees. See that? And there's another one. And then most substances will have a complete heating and cooling curve. So you got 2 steps. Most substances. So here I drew one for gold. So what did I do? I went to the periodic table because gold is an element. Here's the melting point. Here's the boiling point. Then there are substances that do not have a complete heating cooling curve. For example, aspirin. You ever open up a bottle of aspirin and it smells kind of like vinegar? Well, here's what's happening. To make aspirin, they start with salicylic acid, which is originally was found in the bark of a willow tree. So the willow was a very, how do you say, well-known tree because it could cure pain. We also found salicylic acid in the bark of mountain apple tree several years ago in Hawaii. Anyway, so this is a little bit too harsh on people's stomachs. So what the Bayer process was, they took acetic acid and hooked it on right here. And that's what aspirin really is. Acetyl, which is this part, which is that part, salicylic acid. But when there's water involved, you can hydrolyze off of that and you end up getting acetic acid, of which vinegar is about a 5% solution of acetic acid. So to prevent the breakdown of aspirin, they oftentimes will put a desiccant in there. And what this does is it absorbs the water. So inside your closed aspirin bottle should be 0% humidity. And they have to put do not eat on these things. You know why? Because of surfers. I know, my friends are surfers.
What do they do?
This is the mentality. It's like, okay, so you buy a bottle of 100 pills and of aspirin, and here's one really big one in there. And they're thinking, oh, well, if you have a really bad headache, then you take that one.
Oh, God. I have a question. What is that thing called? The sorbet can do not eat. What is that called?
It's a desiccant. It simply absorbs the moisture out of the air.
How much moisture could it absorb?
Well, it depends on how much is in there, but it could easily absorb all of it in the aspirin container.
Right. But like if you were to put it like in a room, I don't know. I'm just thinking of like if you were to drop it in a cup of water, like that wouldn't work.
No.
Okay.
Yeah. You have a dehumidifier in the next room over there, and I got to empty it every day. We're in an air-conditioned building. I don't want mold growing on the walls and stuff because we do cell culture in there. And I got to empty it every day. It's several gallons every day.
Oh, wow.
So then solids, two major types. We have amorphous solids or polymorphic solids. Glass is one. For example, you can melt it, it gets soft, melt it some more, it gets softer. You can make stuff out of it, right? Plastic, GAC, all those things, they don't have sharp melting points because they don't have a single distinct attractive force. So when you heat them up, you break the weaker attractions. You heat them up a little bit more, you break the next stronger ones. Does that make sense to you? So I remember when I was a very bad brother. So I had sisters, I didn't have another brother. And they had Barbie dolls, and I found out that you could do some amazing things with Barbie dolls. So there was, hang by the neck until dead Barbie. There was like, Barbie was behind Dad's pickup truck. And there was Barbie's head on Ken's doll. And then I found later on that you could put them in boiling water and you could stretch them really well. So there was stretch Barbie, there was contortionist Barbie, because they're amorphous. But most solids are what we call crystalline solids. And so a pure crystal will have a very sharp melting point because there's only one type of attractive force. So here's an example. If I have a pure crystal of sodium chloride and I look at it under the microscope and I heat it up very, very slowly, I see nothing happen. And finally I get to 801 degrees and bam, just like that, the whole thing melts one time. Only one attractive force. Then, if I take an impure crystal, say I have water in the crystal, now I have attractions between water and water, water and sodium, water and chloride, and sodium chloride. When I look under the microscope and I slowly heat it up, it starts to melt way before 801 degrees. And it doesn't melt right away. It melts kind of like, it's like there's variable different melting points to it. So anyway, the way we describe crystalline solids is by the type of lattice point. So students have a hard time, what is a lattice point? Well, let's look at an ionic crystal. Here's sodium chloride. What if I'm in a little tiny spaceship and I'm trying to drive through this crystal of sodium chloride? What am I driving around? I'm driving around ions. So the lattice points are ions. That's why it's called an ionic crystal. Then the melting points are going to be very high because the attractive forces are ionic bonds. Well, what about water, for example? So here I'm in a little spaceship and I'm driving through here. What am I driving around right here to get through there? Water molecules. So they're molecules. They're molecules. That's why it's a molecular crystal. And the melting points are going to be low to medium because the attractive forces are London's dipolar and hydrogen bonds. And finally, what if we're driving through a crystal, like here's diamond, and I'm driving through here. What am I driving around? What are the lattice points? They're atoms, okay? So it's an atomic crystal. So right now, in our class, we're gonna say there's 3 categories: ionic, molecular, and atomic. That's all. Now you notice in the parentheses, there's other terminologies. I'm telling you, it's like a mess out there on the internet and in different textbooks. But within, the way to organize it, the way I've done it, within atomic crystals, we have different types, subtypes, right? It could be covalent or network, it could be metallic, or it could be noble gases. So let's just try to get an idea of that. Here's a metallic crystal. So I'm in my little spaceship driving around these lattice points. What are the lattice points? Well, they're atoms. Well, what's holding them together? The metallic bond. That can be low to very high melting points. What about noble gases? Look on the periodic table. You will see listed the melting points. So in the solid, what are you driving through? Atoms.
So a lattice point is how these atoms are connected?
No, they are what are the things that actually occupy space. Not a bond, not in between atoms, but what is occupying the space.
Okay.
So I'm driving through this crystal and notice that carbon here is tetrahedral. And diamond is 3-dimensional. But if I'm driving through here, I'm driving around atoms. They happen to be all covalently bonded together, so that's why they often call them covalent crystals. But really, we're calling them atomic crystals first.
And therefore, for the ionic bonds, the lattice points are the ions. It's the atoms and the electrons that are occupying the space of the crystal.
Exactly. Yep.
Okay.
Then while we're at it, we might as well look at the difference between diamond and graphite. Graphite is where every carbon is bonded to 3 other carbons, so there's a double bond in there. And so planar trigonal, you get these flat sheets. It's just 2-dimensional compared to tetrahedral, which is 3-dimensional. So these flat sheets of graphite can slide around on each other, so making them a very nice lubricant type of thing, or locks and things like that that you don't want to get all gummy from oil-based lubricants. So this is a interesting site over here. It zooms in really close and it zooms out really far. It's really an interesting thing. I would suggest you look at it. So here's an electron microscope image of a computer chip, okay? Because we were talking about silicon, right? So anyway, silicon is a semiconductor, and how do you produce these lanes for the electrons to travel through? You get a positive charge over here and a negative charge over here, then electrons are going to be pulled this way, right? But how do you make the lanes? So what you're really doing when you make a computer chip is you're making this really, really tiny conducting pathways. So what you do is you create basically blockages using silicon dioxide. So you oxidize the silicon right here with oxygen, but not here. It's kind of interesting. You should look at this site right there. So what is a mineral? A mineral is a naturally occurring substance that can be represented by a chemical formula. So we talked about tokyoite in chapter 11. Topaz, which is a really beautiful mineral, is this formula right here. And then what is a hydrate? Well, some solids are hygroscopic. They absorb water from the air. So here's an example, because it's an everyday example. This is called plaster of Paris. Oftentimes they will write the structure to get rid of the 1/2, they multiply the whole thing by 2. So 2 calcium sulfates for every 1 water molecule. So I'm sure you worked with plaster of Paris. I think everybody that grew up in Hawaii, I think it's mandatory that in elementary school you make a volcano. I was so happy to see that my grandson did that, because I asked people and they, oh, we never got a chance to do that. Okay. So what is plaster of Paris? It's like this white powdery stuff. So it's a solid, but it contains a water molecule in it. Then you took the plaster of Paris and you mix it up with water and then let it harden again, and it turned into gypsum. It took 2.5 more water molecules per formula unit of calcium sulfate to make calcium sulfate dihydrate. It's a solid. This is what they use to make drywall out of. So they sandwich it between 2 pieces of paper, right? And it's a solid. That's what double wall houses are made out of. Here's another example, one that's easier to use in a desiccator. So what you're trying to achieve in here is 100% humidity. And I have some chemicals that I have to store them in desiccators like this. So what we do is we take something like copper sulfate, the anhydrate, It's a light blue solid. When it comes into contact with water, it absorbs it and turns into the dihydrate, which is a dark blue. So it's a good indicator as well. So if I put my chemicals that I want to keep at 0% humidity in here, as long as I see that the powder that's in there is a light blue and not a dark blue, I know that I can still absorb lots of water. If I see that there's still some blue stuff, light blue stuff in there, I know that's 100% humidity in there. And this will absorb water instead of the molecule I'm trying to protect. Anyway, and that's the idea with that little dehumidifier thing that they put into bottles of pills, right? Same concept. So now, what about attractive forces? What are the effects of having strong attractive forces? Well, one, you're going to have a high melting point, right? You're going to have a high boiling point. And now I need to make sure that you know the difference between boiling and evaporation, because both of those processes are going from the liquid to the gaseous state. So what is the definition of boiling? You heat up the liquid until you see bubbles forming that rise to the top, right? What is the definition of evaporation? Molecules from the surface go into the vapor phase from the surface. Now that we've said that, when you boil water, what's inside those bubbles?
Heat?
Heat is not a substance.
It's gas, right?
It's a gas, yeah. What gas could it be?
Oxygen,
No,
hydrogen.
it's water. Here you're going from liquid water to gaseous water. Here you're going from liquid water to gaseous water. What if I boil alcohol? What's in the bubbles?
Alcohol.
Right? Yeah. And so here's some heating curves for three substances. Here's water, which has hydrogen bonds. Here's ethanol, which has hydrogen bonds, but less of them. And here's acetone, which has only dipolar attractions. So look at the normal boiling point, which is at 1 atmosphere. Which one would you tell me has the strongest attractive forces? Water, right? Now we can understand what distillation is. Most of the time, when we talk about distillation from person to person, we're talking about alcoholic drinks, right? Hard liquor. And so beer and wine can only go to a couple of percent alcohol, because after that, it actually kills the microorganisms that produce it. So if you want stronger amounts of ethanol in your drink, then you have to go through distillation. So here you have a water and ethanol solution. You heat it up, and then the vapor phase over here contains both ethanol and water. But which one is preferentially going to evaporate? It's going to be the ethanol, isn't it? So the boiling point of ethanol is about 78 degrees. So when I first start this, and I want to be careful not to just start boiling this rapidly, but I want the vapor to be preferentially ethanol up here. So the vapor just drifts over here, and now this becomes a coolant. So you put cold water in here, so now it condenses and drifts over here, you're going to get ethanol. When I get significantly amount of ethanol coming out already, I'm going to notice that the temperature is going to start to go up. When all the ethanol is gone, then I'm going to be reading 100 right here. And I'm just distilling water over. So there will be some point when the temperature starts to go up that you stop and say, no, I'm not going to do this anymore because I want this to be a certain strength over here. So if you have strong attractive forces, you're going to have what's called a low equilibrium vapor pressure. So I guess I have to explain to you what is equilibrium vapor pressure. So here I have a flask, a cork, and I put a glass U-tube in here. And when I first put this together, I put some mercury in here. The mercury levels would be just like this. That would mean that the pressure pushing up this way is equal to the pressure pushing down this way. So then I add water in here. And after a little bit, the water is going to start to evaporate. And when it does that, besides the nitrogen and oxygen and whatever else in the air, it's adding a new gas. So the total pressure goes up. So I'm pushing up here, which pushes the mercury down over here. And now I get a difference in mercury. And that difference in millimeters of mercury is the vapor pressure. So the more vapor you have up here, the greater the vapor pressure. So if I were to put a solid in here and try to measure the vapor pressure of a solid, I'm going to get none, right? If I put a rock in there, it's not going to give me any vapor pressure. If I put water in here at 20 degrees, I'll get 18 millimeters of mercury. If I put acetone in here, I get like 10 times that amount. What does it have to do with attractive forces? The stronger the attractive forces, the lower the equilibrium vapor pressure.
The stronger the attractive forces, the lower the vapor pressure.
Exactly. Because it's harder to get into the vapor phase, right? Harder to evaporate.
So the vapor phase would be lower.
Right. Mm-hmm. Okay, so higher temperature produces higher vapor pressure. And so I drew this. I couldn't find anything I wanted on the internet. This is the closest thing I could find. But look at this, what I drew here. So here's the number of molecules. Here's the kinetic energy or the temperature, right? And here's the transition between a liquid and a gas. Now look at T1. What you have represented by this curve right here is that not every molecule has the same kinetic energy, right? It looks like some kind of a Gaussian distribution over there. So at this particular temperature right here, this average temperature right here, what's going on is evaporation. These small amount of molecules right here have enough kinetic energy to go from the liquid to the gaseous phase. You see that? Only these ones. So which molecules will go from the liquid to the gas? The ones with the most kinetic energy. Now what happens if I raise the temperature? Well, now I see most of the molecules are able to go into the gaseous phase. Not all, but most. I would say that's boiling, or this was evaporation. So now, why do we sweat? And I'm sorry to say that. I know women don't sweat. They perspire very gracefully. And men sweat like pigs. But in fact, pigs don't really sweat. That's why they're always trying to find cool places to wallow in. But anyway, why do we sweat? Because when we put water on the surface of our skin, which of the molecules are going to go and evaporate? The ones that have the most kinetic energy. So what you're doing is you're removing kinetic energy from your body, which lowers the temperature. It's all kinetic theory throughout. So what is relative humidity? Well, it's simply uncomfortable, but it's not hot. Here's what relative humidity is. It's the actual partial pressure of water vapor that they measure, and they compare that to the maximum possible at those conditions. That's what that means. So now I think we could talk about what's called freeze drying. Freeze drying, you don't need a freezer. So say I had a glass of water and I put it in this vacuum chamber and I turn on the vacuum pump. What's going to happen? First, there's going to be evaporation from the surface. I might see a little bit of boiling, depends upon how strong the vacuum pump is. But mostly I'm going to see evaporation. And evaporation of which molecules? The ones that have the most kinetic energy. So those kinetic energy containing water molecules are basically sucked out. What we're doing is sucking kinetic energy out of this container. And eventually the temperature goes down and the liquid freezes, turns into a solid. And then what happens? It's sublimation. You go from the solid to the vapor directly, and then whatever gets into the vapor phase is sucked out by the vacuum pump. The vacuum pump is trying to maintain 100% humidity over here. So what would happen if you're in outer space and it's cold and there's like pretty much zero atmosphere? Just like you're going to step right into a vacuum pump. You'll be dehydrated and frozen and sublimed in a few seconds. Then if you have strong attractions, the liquid will also have high surface tension. So this is a pretty good depiction over here. Say this is water because that's the easiest for it to think about. So this molecule down here is being pulled in all these different directions by the hydrogen bonding from the other water molecules. But what about this one on the surface? There's no attractions over here, right? So but it has its same magnetic field, but now it's focused on only a couple of directions. So the attractive forces here are a little bit stronger. So look, cold, smooth water, the surface tension can be important. Here's another depiction of that. And this water bug right here is taking advantage of that surface tension, isn't it? Did you ever jump off a waterfall into cold, smooth water? And you really experience the surface tension. but yet you can jump way higher into the ocean and it's not as bad. Because look at the surface of the ocean. The water is just moving all over the place. And what is that doing? It's breaking these attractive forces, constantly breaking them. And if you have strong attractive forces, then you're going to have a high heat of fusion, heat of vaporization, specific heats. And all I did was compare water and acetone. And this is the kind of thing not in textbooks, so I had to make this up, and I was surprised to see that it was so dramatic, actually. Acetone is quite a bit heavier than water. But look, all these values are just much larger for water because they all have something to do with attractive forces. So attractive forces cannot explain the appearance of something, the odor of something, or other properties like even density. People would think that, oh, strong attractive forces means that they pack together tightly. Not necessarily, because that has so much to do with shape of things. Okay. So here's some examples. Water boils at 100 degrees and ethanol at 78.5. Which one should have the highest surface tension? And I tell you what, I think a lot of people that are chemists even, you show them that, they're going to like, what? They're not even related. The answer is, yes, they are related. And the relationship is attractive forces. So looking at the boiling points tell me that water has stronger attractive forces. Therefore, it's going to have stronger surface tension. So compound A boils at minus 82. What can you tell me about it? Well, at normal temperatures, it's going to be a gas. It should have a low melting point, a low boiling point, a high vapor pressure, a low surface tension, low heats of fusion and vaporization, and heats of all phases, specific heats. What if we compare these two compounds? Okay, well, B also will be a gas at room temperature, but compared to A, B should have a higher melting point. Where am I? Higher boiling point, and lower vapor pressure, and higher everything else. Okay, so you get the point? It's about attractive forces. I'll do more. Yeah, so here's some chemistry humor, and I saw this on the internet, and I'm like, oh my God, I gotta use that for something. And I just love this one. It's called irony. Yeah. Okay, so any questions on chapter 16? I'm glad we're getting into chapter 17 today. So we know what a solution is. We know what a mole is. We know what a liter is. So we pretty much got this together. We just have to look at it in detail. So molarity is given the symbol capital M. It means moles of solute per liters of solution. So solute is the thing that you're dissolving into the solvent. Did I say that right? Solute is what you're dissolving into the solvent to make the solution. So if I'm taking sodium chloride and dissolving it into water, you can tell which one is which, right? So
Can you say that one more time?
if I'm taking sodium chloride and dissolving it into water, then water is the solvent, and sodium chloride is the solute. So what does
Maybe
it,
like hot cocoa powder and water. Hot cocoa would be the hot cocoa powder would be the solute, and then hot water would be the solvent.
solvent, yeah.
Oh, okay, I got it.
Sweet analogy there.
Yes.
So what does it mean to say you have a 0.2 moles per liter solution of sodium sulfate? That means that there's 0.2 moles in every liter, 0.4 moles in 2. Look at this. This is a direct proportion. I graphed it. The slope of this line is the conversion factor. So in chapter 18, we go through a whole bunch of different kinds of other concentrations. But it doesn't matter. The concentration is always going to be your conversion factor. You're converting between one thing and another thing. That's it. No matter what it is. This could be grams. This could be milliliters. See what I'm getting at? And it's all a direct proportion. So how do you make 4 liters of a 0.2 moles per liter solution? Well, you got to calculate how much solute you need. So I need 4 liters at 2 moles per liter, so I have to put 8 moles of solute in there, 0.8 moles of solute. But I can't weigh out moles, I can only weigh out grams, so I need the molar mass to convert moles into grams. So I calculated I need 114 grams, so what do? I put it into a graduated cylinder, which is something like we looked at earlier, right? And I add a little bit of water to dissolve the solid because I want to get rid of any volume changes that happens when you dissolve it. And I want to get rid of any temperature changes that happen when you dissolve it. Some substances, when you dissolve them in the water, it makes the water warmer. Sometimes it makes it colder. And it's hard to predict. Just because you add something to a liter doesn't mean that the volume goes up. It may also go down. So you dissolve it, and then you fill it to the top. And you want the bottom of the meniscus to be on the 4 liter line. And then you stir it to make sure it's homogeneous. So now maybe you're wondering, what the heck is a meniscus? And by the way, the meniscus is not that half human, half horse dude that used to hang out with Xena the Warrior Princess. That's a minotaur. So the meniscus, or the smile, happens because if you look at what's happening, and you can look at this in a glass of water, you see the same thing. The meniscus is running up the surface of the glass. What that means is that the water is attracted to the glass. In fact, glass is a nearly ionic solid. It's about 45% ionic character. So water is attracted to it, but it can't dissolve it. If you look at a drop of water on glass, it kind of sucks down onto the glass. If you look at a drop of water on plastic, it beads up. So when you put Rain-X on your window for your car, on your windshield, what is it doing? You're putting a plastic barrier there so it doesn't do this. It beads up like this and then rolls right off. if you look at in a test tube, for a glass test tube, meniscus goes up like that. For a plastic meniscus, it goes down. And most people will look at this and say, oh, that's because the plastic is repelling the water molecules. And the answer is no. Like I said, how many times before, everything is about attractive forces, and attractive forces are much more important than repulsive forces. If you look at over here, there's lots of attractions going to the glass, but there's still attractions within the water molecule. They're still attracted to each other by hydrogen bonds. If you look at the plastic, there's not much attraction to the plastic. It's only London's attractions compared to hydrogen bonding in the drop here. So it beads up like that. So the inverted meniscus in plastic is not because of repulsive attractive forces, it's because of attractive forces. So we can do problems like how many moles of sodium sulfate in 25 milliliters of a 0.2 moles per liter solution? Keep in mind that that is my conversion factor right there. So this is moles per liter, so I had to convert 25 milliliters to liters. Then get rid of liters, keep moles, there's my answer. What if they ask how many grams in that same situation? I just got one more conversion step, right? Convert moles into grams using the molar mass. How many milliliters of a 0.2 moles per liter solution of sodium sulfate are needed to get 1 gram of sodium sulfate? That's my conversion factor. How do I start the problem? 1 gram of sodium sulfate, I just write it down. And I'm thinking the conversion factor has moles, not grams, so I have to convert grams into moles. Then I can get rid of moles and keep liters. Make sense? Then I just convert it into milliliters. So, you can see the methodology that we started from day one. Here we are almost at the end of the course and we're still using the same math. So this next thing is dilution problems. And here's why it's important. And I really do not understand why textbooks just don't do it. It's crazy. How many doctors and nurses do we have taking chemistry courses in college? This is like crazy. They don't do dilution problems. But they're very important in medicine because drugs are stored as concentrated solutions. And then they have to be diluted into the volume of the patient. So some drugs not that critical. So you take 1 or 2 tablets of, say, ibuprofen or something, right? Based upon your body weight or age or something. But I can tell you there's been a lot of medical lawsuits against nurses. If you're an RN authorized to give medicine and you simply follow the doctor's orders and you either give the wrong dosage or the wrong medicine, even though you're just following doctor's orders, you are legally liable for medical malpractice. Half of the job.
What should an RN do in that situation?
I'm sorry?
What should an RN do in that situation?
Know what they're doing.
Uh-huh.
So half of the RN's job is to protect the patients from the doctors. You've been to the doctors. How much time do they spend with you?
Like nothing.
Yeah, it's a joke.
It seems kind of funny that the nurses actually have to take that responsibility and the doctors don't.
There has been a few lawsuits where the doctor, they didn't even go after him. They went after the nurse.
That's crazy.
I know.
Seems a little messed up.
Welcome to world.
Right.
So anyway, I'm going to go through where the dilution equation comes from. So here's a concentrated stock solution. And here's something that we're going to dilute by adding water to it. So notice how simple this is. The moles that I take out of here is equal to the moles that I put in here. And then I'm just adding water. So it gets diluted, right? Less concentrated. So look at how we derive this. The moles that we take out of the concentrated solution is equal to the moles that we put into the diluted solution. But we could calculate by saying moles per liter times liter of what we took out, and then equal to moles per liter times a liter of where we've done our dilution. Then I can just kind of codify moles per liter into M. And then, does it really have to be liters? Does it really have to be moles per liter? No, it could be osmoles, it could be grams, it could be anything. Because solutions are all direct proportions. So this is the most generalized for any unit. So here's the concentrated solution, here's the diluted solution. Now you got 4 variables. If I ask you for one, the problem has to give you the other 3. See how that works? So for a stock solution of 0.2 moles per liter sodium sulfate, find the concentration of a solution by diluting 10 milliliters to a final volume of 1 liter. So what I need to do, similar to the gas problems, is simply figure out these things. So the concentration of the concentrated one was 2 moles per liter. The concentration of the diluted one is, well, that's what we're looking for. The volume of the concentrated one was 10 milliliters. The volume of the diluted one was 1,000 milliliters, right? So algebraically, I just solve for concentration of the diluted one and I plug in the numbers. There it is. You just have to make sure that the units cancel. How much water was added? Well, the total volume is 1,000. I started off with 10, so I had to add 990 milliliters. And then, what is the dilution factor? What? A dilution factor was that we took 10 milliliters and diluted it to a volume of 1,000. That really is the ratio of these 2 volumes, which is really a 1 to 100 dilution factor. Sometimes they show it this way. But we could also now calculate the dilution factor from the ratio of the 2 concentrations. We made a 0.02 molar solution from a 2 molar solution. I could just move decimal places over to get to 1 to 100, but here's another way that we're doing it. I'm taking this one, dividing by itself in order to get a 1, and I have to do the same thing down here. I get a 100. So you can either multiply by the dilution factor or divide by it. There is no other choice. When you do that, one will give you a reasonable answer, and the other is not a reasonable answer. So, using the dilution factor of 1 to 100, what is the concentration of the diluted one? You know, if I have the concentrated one, I'm either going to go 1/100th times that, or 100/1 times that. This one makes sense. This one has no way of being true because that's way more concentrated than you started with.
Yeah, why would you do 100 divided by 1?
Because that's the only things you can do with a dilution factor. It's
Oh, you can either do it. I see.
There's no other thing you can do with it.
Oh, okay. So you
And the
just do.
reason why I'm going in this direction is because when you get to nursing school, this is what they do. It's always by dilution factors. That's why I'm showing you both ways.
Oh, so this is how there can be an issue.
Yeah. So to solve the dilution questions for a stock solution of 3 moles per liter. So how many milliliters of a 3 moles per liter solution are needed to make 2 liters of a 0.1 molar solution? So I just pull out what the variables are. We're looking for the volume of the concentrated one that I'm going to use, right? Plug in the numbers, there's the answer. How much water did I have to add? There's the answer. What is the dilution factor? Notice that this right here is the dilution factor, isn't it? 0.1 to 3 is the same as 1 to 30. But you can see how you get that, huh? And then once you have the dilution factor, then you can see how you can get the other ones using the dilution factor. Because in fact, the dilution factor represents 2 of the 4 variables. So they only have to give you 1 variable, give you the dilution factor, and ask you to solve for the missing thing. Which at the bottom here, look at this problem here. 0.5 milliliter solution was prepared by doing a 2 to 25 dilution. What is the concentration of the stock solution? What are my choices? I can either do a 2 to 25 or a 25 to 2. The 25 to 2 gives me bigger numbers, so that's the stock concentration. See how that works? So that dilution factor represents 2. Here's the 3rd one, and that's the 4th one you're solving for. Okay. So hopefully that's enough dilution problems. It's very difficult to find them on the internet or in a textbook. So when I had Alexandra in the lab for that 1.5 years or so, she was a math professor from a university in France. She was trying to model some of the growth patterns we were finding in cells. And I asked her this question. So I said, look, is the dilution a direct proportion or not? Because it's a straight line, but then what happens over here? And I never got a clear answer from her. But yeah, so maybe it's not a direct proportion, but it acts like one. So I think what I'll do is, we got a couple minutes more. I'll do titrations right now, like maybe the first one, and then we'll do it again tomorrow. Okay. So titrations are stoichiometry problems that use concentrations. So just like any other stoichiometry problem, we're given enough information to do some things, but not the other things, right? We have to calculate them. So here is an acid-base reaction, a neutralization reaction. And what works in here is moles. During stoichiometry, we're like, well, what if we were out here, we got grams? But now with the titration, using liquids, what if we got liters? We measure things out by volume over here. We got liters over here. We want to get moles. What's the conversion factor? Maybe moles per liter. That's our conversion factor. So it's just simply stoichiometry using moles per liter. So a student titrated or neutralized 15 milliliters of sulfuric acid solution with 35 milliliters of a 0.2 moles per liter sodium hydroxide solution. Give the concentration of sulfuric acid in moles per liter. So we need the balanced reaction. And then the problem gives you enough information to calculate moles of either the acid or the base. So look what we have here. Here's for the acid. Here's the volume. They don't give us the moles per liter. We cannot calculate moles of the acid from that information. What about the base? Here's essentially the liters. Here's the moles per liters. We can calculate the moles of the base. So I'm going to do that. I'm out here. I'm going to go in here by one conversion factor. So I convert volume into moles, right? So there's the moles of sodium hydroxide. I'm in here now. How do I get here? I use stoichiometry. So I got this many moles of sodium hydroxide, but that stoichiometry tells me that there's 1 mole of sulfuric acid for every 2 moles of hydroxide. So now I got the moles of the acid. But there's enough information now to calculate the volume. I mean the concentration, because I have the volume. I got this many moles of acid that was in 15 milliliters of water. Or not water, but of solution. So here's the moles, here's the liters, there's the moles per liter. So here's what we did in this titration. I took 15 milliliters of the acid. I don't know its concentration. I took a burette, which is a very glorified and high precision pipette, essentially, and I filled it up with 0.2 moles per liter sodium hydroxide. And I dripped it in here until I knew the reaction was over. Think about pH now. This would be a low pH. This would be a high pH. If I put a pH meter in here, I would be measuring a low pH. Then I'm dripping this in, and the pH starts to go up. And how do I know when the reaction is over? It should be pH 7. So I hit pH 7 after I had put in 35.20 milliliters of the base. So I had to put in 35.2 milliliters of this to neutralize this. Make sense? So it's really just stoichiometry. Now I also did something different here. Most of the time students don't see stoichiometry until the chapter on acids and bases. And then they think that, oh, titrations are only about acids and bases. And the answer is no, it's not. It could be any kind of chemical reaction. You know what one of my favorite titrations is? Well, here's a couple of examples of titrations. You make a cup of coffee, You put in some cream, probably you're titrating it till you get to a certain color, right? You're titrating the color. And then you put in a sugar, you stir it up, you taste it. Maybe you need more sugar, so you put in, that's titration. How much of one do you have to have for how much of the other one that's there? My
So-
favorite titration is when you go to buy something at a store and you have like a Japanese tourist in front of you or something. And that Japanese tourist is essentially titrating the cashier. They don't know the money system. So they put what they want to buy on the counter, then they put some money, and then they look at the cashier, and from that, they decided if they need to put more money or not. You're essentially titrating the cashier. So that's all we're doing here. Same thing. So you had a question?
I was gonna say it's almost like percents, right? Like percentages, like that you're just like mixing up.
I can see I can see the analogy if you're like adding something until you get a certain result. Yeah.
Yeah, I was using that for the coffee example, and then
Yeah.
I talking about money.
Money is usually a good analogy for everything.
Hmm.
So, anybody have any other questions? Okay, well, don't forget you have your exam to do today and tomorrow, yeah?
I have a question that I ask you after. It's unrelated to this class.
Okay. And you don't want it on the recording, so.
I mean, it's fine. I was just wondering about what the next quarter will be about. So it's
Well, you know what? We're almost done with Unit 4. In Unit 5, a lot of the Unit 5 we've actually already covered. And I may have to cut Unit 5 a little bit short, especially on homework and stuff. But yeah, we'll talk about that later in the week, though. Does that answer your question?
yes, and then also I'm like having trouble registering for 341 because I don't have the prerequisite or something, and so I was wondering if you could help me with that.
Oh, yeah. Just send me an email to remind me, will you? And I'll
Okay.
just an override for you.
Okay, great. Thank you.
Yeah, sure.
I actually have a question, Professor.
Sure.
So the reason why I'm taking biochemistry, aside from my love of chemistry, is because it's a prerequisite for grad school for me.
Yeah.
Would I need to take both biochemistries to have that fulfilled? Do you know?
Well, are you doing it in Hawaii?
No, I'm not.
Okay. Well, I have no idea then, but then it would also depend upon your major.
Yeah,
So what is your major?
I'm a kinesiology major, so it's not for the major. It's purely for the grad school. And a lot of I'm going into the PA program, or I'm trying to get into the PA program, and a lot of them require biochemistry.
Physician's assistant?
Yes, sir.
Oh, yeah. You got to know more than nurses do. So yeah, you need it.
Yeah.
Yeah. So you do need a biochemistry course.
So so this wouldn't count, or?
Well, you might trick them into making it count, but if they knew what was covered in this course compared to 341, they would make you take 341. Yeah, definitely. Yeah, especially for the PA route.
Yeah.
Yeah. So, but then again, you know, I've had students get into med school from taking only the 241, and essentially because that particular med school didn't know what was in the courses.
Yeah. Like, don't get me wrong. I want to take the next one, but I'm also taking like 2 other classes this next summer session, so I don't think I can.
Yeah. Well, depends what you got to do, what you got to do, right?
Yeah.
Is next quarter also completely online?
Unfortunately,
Okay.
yeah. Like similar to this course, I wrote all the chapters and everything, but for that course, I've never taught it online before, so it's going to be more difficult.
But it's for sure like not going to switch to be in person at the end or anything because I'm out of state right now, so I'm just
No, it's all online.
okay. Okay.
Yeah. When you said out of state, I'm thinking, oh, gaseous, liquid, or solid. Yeah. Are
What
you
kind of
out of
material?
state because of the virus?
Yeah, I wasn't able to come home. Well, I decided not to come home last minute because of everything. So I'm staying in where I go to school in California.
Yeah, that's hard.
Yeah.
Aruna, did you have a question?
Sorry, I was wondering like what kind of material will 341 cover next semester?
We start off with organic chemistry. So I don't do the hardcore organic chemistry. It's just the basic chemistry of the functional groups. And then we go into the organic chemistry of biological molecules like carbohydrates and proteins and lipids. And then we go into real biochemistry of proteins and, yeah, DNA, RNA, molecular biology. I wrote a chapter on diseases, applying biochemistry to diseases. I wrote a chapter on applying biochemistry to nutrition, which I'm not sure we'll get to it, but we'll try. So it's really applications at the end of the course.
Is it a lot harder than 241?
Some people struggle with organic chemistry. Some people don't. So it's hard to say. That's really hard to say.
Got it. Thank you.
Okay, anything else? Okay, well, you guys have a great day, and I will maybe see you tomorrow.
You too.
Thank you.
Thank you.
Take care. See you.